Piping vibration. Good design practice for piping systems, key principles ensuring safe and efficient pipeline layouts. Purpose and context of good design practice. This good design practice refer to Energy Institute guidance for piping systems. It is essential to prevent vibration-induced fatigue, which can lead to structural failures, operational inefficiencies, and safety hazards. Vibration fatigue occurs when cyclic stresses from fluid flow, mechanical forces, or operational dynamics cause cracks or fractures in piping components over time. This technical module, T13, provides a summary of key principles to mitigate these risks. It emphasizes the importance of considering vibration effects during the design phase rather than addressing them reactively after installation. By implementing these practices, engineers can ensure system reliability, reduce maintenance costs, and enhance safety. The guidelines also reference TM05 and TM06 for detailed examples of good and poor practices, reinforcing the need for practical application. Understanding these principles is critical for industries such as oil and gas, chemical processing, and power generation, where piping systems operate under high pressure and dynamic conditions. The overarching goal is to design systems that maintain structural integrity, minimize vibration transmission, and accommodate operational stresses without compromising performance. This involves a holistic approach that considers layout, support mechanisms, material selection, and component configuration. Ultimately, adherence to good design practices not only extends the lifespan of piping systems but also ensures compliance with industry standards and regulatory requirements, fostering a culture of safety and efficiency in engineering projects. Key principles for main line layout and support. Designing the main line of a piping system requires careful attention to layout and support to minimize vibration-induced fatigue. First, adequate guides and line stops should be incorporated wherever practicable to restrict unwanted movement and maintain alignment. Long sections that are vulnerable to large transient deflections must be avoided, as these can amplify vibration and lead to structural damage. Reducing the number of bends is crucial because each bend introduces stress concentration points. When bends are necessary, supports should be placed as close to them as possible to prevent excessive movement. Additionally, bends should be spaced at least 10 pipe diameters apart to allow for smoother flow and reduced turbulence. Long radius bends are preferred over short radius or mitered bends because they minimize pressure drops and vibration effects. The stiffness of clamps and supports must be sufficient to restrain the piping effectively, preventing oscillations that could compromise integrity. Heavy masses such as valves should always be supported to avoid creating cantilevered loads that exacerbate vibration. The span between supports should be carefully calculated to prevent long unsupported lengths, which can act as vibration amplifiers. Spring hangers, while sometimes necessary, should be minimized because they introduce flexibility that can worsen vibration issues. Finally, a wear-resistant or compliant layer should be inserted between the pipe and its supports to reduce friction, absorb shocks, and prevent localized wear. These measures collectively ensure that the main line remains stable under operational conditions, reducing the risk of fatigue failures and enhancing system reliability. Design strategies for small bore connections. Small bore connections, SBCs, are particularly susceptible to vibration-induced fatigue due to their relatively small size and cantilevered configurations. To mitigate these risks, fittings and overall unsupported length should be kept as short as possible, reducing leverage and stress on the connection. The mass of valves and instrumentation attached to SBCs should be minimized, ideally by using lightweight components such as double block and bleed valves or monoflange valves. Any mass located at the free end of the cantilever must be supported in both directions perpendicular to the axis of the connection to prevent oscillation. Bracing should always originate from the parent pipe rather than surrounding structures, ensuring that vibration forces are absorbed by the main system rather than transferred externally. Increasing the diameter of SBCs enhances stiffness and reduces susceptibility to vibration. Short body contoured fittings, preferably one-piece forgings, are recommended over weldolets and nipples because they provide superior strength and durability. Threaded connections should be avoided entirely, as they are prone to loosening under vibration, leading to leaks and failures. Instead, bolted clamps designed for vibration resistance, incorporating anti-vibration washers or lock nuts, should be used to secure components. These practices collectively improve the resilience of SBCs, ensuring they maintain integrity under dynamic operating conditions and reducing the likelihood of costly downtime or safety incidents. Best practices for tubing systems. Instrument tubing systems play a critical role in transmitting signals and fluids for monitoring and control, but they must be designed to withstand vibration and movement from the main piping line. To achieve this, sufficient bends or pigtails should be incorporated into the tubing layout, allowing flexibility to accommodate main line movement without imposing excessive stress on connections. Any mass attached to the tubing, such as valves, gauges, or instruments, must be well supported to prevent sagging or oscillation that could lead to fatigue. All supports should be verified for effectiveness, ensuring they provide adequate restraint under operational conditions. The tubing system should be designed according to recognized standards, using appropriate components that are compatible with each other. Mixing fittings of different types or incorrect assembly practices can create weak points that fail under vibration. Proper installation techniques, including secure fastening and alignment, are essential to maintain system integrity. Reference should be made to established guidelines such as the Guidelines for the Management, Design, Installation and Maintenance of Small-Bore Tubing Systems to ensure compliance with industry best practices. By following these principles, engineers can create tubing systems that are robust, reliable, and capable of enduring the dynamic forces present in industrial environments, thereby safeguarding instrumentation accuracy and operational safety.